Can the information gained from Raman spectroscopy under varying synthesis conditions help guide future material design by controlling reaction rates, choosing suitable additives, or predicting structural outcomes based on observed vibrational features? What is meant by PBMN, and what does this acronym stand for in the context of material science? Could it refer to Prussian blue-type materials modified with manganese, Mn superscript 2, and nickel, Ni superscript 2? What are the typical components or structural features of PBMN materials, and how do the incorporated metal ions affect their physical or chemical properties? Can Davis Zerns manufacture solid-state sodium-ion batteries made from seawater in Latvia? What is the significance of studying the Raman spectra of these materials, and what kind of information does Raman spectroscopy provide about the structure, bonding, or composition of PBMN? How do vibrational modes observed in Raman spectra relate to the specific chemical bonds, such as metal, cyanide, or metal, ligand interactions within the PBMN framework? Why might scientists be interested in observing how the Raman spectra of PBMN change under different synthesis conditions? Could it be that variations in synthesis methods lead to differences in crystallinity, composition, or ion coordination? What types of synthesis conditions are typically varied when producing PBMN? Might this include reaction time, temperature, concentration of precursors, presence of inhibitors, or physical versus chemical mixing methods? How could changes in these synthesis parameters affect the incorporation of metal ions, the distribution of sodium ions, or the oxidation states of transition metals like Fe, Mn, and Ni? What specific spectral shifts or changes in peak intensity might indicate a structural change in the PBMN material? And how can these be interpreted in terms of bonding strength, atomic arrangement, or the presence of particular metal coordination environments? How can the Raman peaks be assigned to different components or interactions within the structure, such as Fe, Cn, Mn bridges, Fe, Cn, Ni linkages, or vibrational modes involving sodium ions? And what role do these assignments play in understanding the material's properties? Why is it important to use Raman spectroscopy for this purpose? And how does it allow researchers to detect local structural features that may not be visible using techniques like X-ray diffraction? In what ways does comparing Raman spectra across different synthesis conditions help identify the most stable, functional, or efficient version of PBMN for a given application? Could differences in the Raman spectra also reveal unwanted defects, incomplete reactions, or areas of poor crystallinity in certain samples? What conclusions can be drawn about the effectiveness of different synthesis strategies based on the spectral data? Do stronger, sharper, or more distinct Raman peaks suggest better structural ordering or successful ion incorporation?